Hello there, and welcome to the Sleepy Space Channel. Of all the worlds the Sun keeps, one is dangerous in every direction at once, and the contest is not close. Jupiter can end a human life in minutes with radiation alone, before its clouds, its pressure, or its gravity ever get their turn. It has no surface to land on, storms that have outlived every nation on Earth, and an invisible magnetic field that would dwarf the full moon in our sky if we could see it. Its gravity stunted one planet, scattered the makings of another, and still steers the comets crossing our sky tonight. Over the next 2 hours, we will take the honest measure of every one of those dangers in turn, and find out why Jupiter stands alone, the scariest giant by far. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Jupiter is far away tonight, and it asks nothing of you. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. There are 2 Jupiters. One of them is the planet you can see tonight, if the sky is clear. It is a bright, steady, cream-colored point of light, one of the brightest objects in the entire night sky. It does not twinkle the way stars do, because it is near enough to show a true disk, and that small disk of light holds steady while the stars around it shimmer. On the darkest nights, away from every city, that single point of light is bright enough to cast a faint shadow on the ground. After the Moon and Venus, it is usually the brightest thing the night has to offer. It looks calm. It looks patient. It has looked that way to every generation of human beings who ever turned their eyes upward. The other Jupiter is the one this episode is about, and it is a stranger and darker thing. Behind that serene point of light stands the most dangerous world the Sun has ever kept. It is a place with no ground to stand on, wrapped in storms older than nations, wrapped again in an invisible field that fills a region of space larger than the Sun itself, and soaked in radiation intense enough to end a human life in minutes. It is a world that has swallowed comets whole, redrawn the map of the solar system, and quietly decided which planets were allowed to finish forming. The gap between how Jupiter looks and what Jupiter is may be the widest gap in the sky, and tonight we are going to cross it slowly, one honest measurement at a time. None of what follows is speculation, and none of it is drama. It is simply an accounting, taken at a comfortable distance, of what the largest planet actually does. The accounting begins with size, because every danger this world holds flows downstream from a single number. Jupiter is roughly 11 times the diameter of Earth. If Earth were a coin resting on a table, Jupiter would be a dinner plate beside it. By volume, about 1,300 Earths would fit inside it. That number is worth sitting with for a moment. Imagine our entire planet, every ocean and continent, and every person who has ever lived, reduced to a single marble. Now imagine a jar that holds 1,300 of those marbles. That jar is Jupiter, and even then the picture is too gentle, because a jar has a lid and a floor, and Jupiter has neither. Mass tells the story more honestly than volume does. Jupiter weighs about 318 times as much as Earth. But the comparison that matters most is not with Earth. It is with everything else at once. Take every other planet in the solar system, from Mercury out to Neptune. Add every moon, including our own. Add every asteroid in the belt, every comet, every scrap of drifting ice and stone that circles the Sun. Put all of it together on one side of a scale, and put Jupiter alone on the other side. Jupiter outweighs the entire collection roughly 2.5 times over. The solar system, seen honestly, is the Sun, then Jupiter, and then an assortment of leftovers, and we live on one of the leftovers. The Sun holds about 99.8% of all the mass in the solar system. Of the thin remainder, Jupiter claims most of it for itself. A world that large might be expected to move slowly, but Jupiter does the opposite. It spins faster than any other planet we know. A full day there, one complete rotation, lasts just under 10 hours. Earth, a world 11 times smaller, needs more than twice as long to turn once. That spin is fast enough to change the planet's very shape. The equator of Jupiter bulges outward, thrown wide by rotation, so that the planet measures about 9,000 kilometers wider across its middle than from pole to pole. 9,000 kilometers is close to the diameter of Earth minus a third. The flattening is real enough to see through a modest backyard telescope. The disk is visibly wider than it is tall, a world spun until it settled into the shape of a slightly pressed sphere. That fast rotation has a gentle consequence for anyone who watches Jupiter from Earth. The great cloud features cross the visible face of the planet in only a few hours. An observer with a small telescope and a quiet evening can watch the famous Great Red Spot rotate into view, drift across the disk, and slip around the far side, all in a single night. Jupiter performs its full rotation for any patient audience, once before midnight and again before dawn. Very few sights in the sky move on a human timescale. Jupiter does, and it always has. The strength of its grip is harder to see, but it can be measured. At the level of the cloud tops, Jupiter's gravity pulls about 2.5 times harder than Earth's gravity pulls at the ground. A person who steps from Earth onto some imagined platform at Jupiter's cloud tops would feel their body weigh 2.5 times as much, all at once. An arm would become a burden. Standing would become labor. And that is only the beginning of the arithmetic, because gravity also sets the price of leaving. To escape Earth, a spacecraft must reach about 11 kilometers per second. To escape Jupiter, it would need close to 60 kilometers per second, more than 5 times faster. Almost nothing that falls into Jupiter's keeping ever reaches that speed again. The planet holds what it takes. It has been holding what it takes for more than 4 billion years, and that patience is written into everything we will see tonight. There is one more measurement worth making before we go closer, and it may be the quietest and most telling of them all. We say, casually, that the planets orbit the Sun, and for the small worlds that is true enough. But gravity is always mutual. When two bodies circle one another, they both swing around their shared center of mass, the balance point between them. For Earth and the Sun, that balance point lies deep inside the Sun, so close to its center that the Sun barely stirs. For Jupiter, the balance point lies outside the Sun altogether, above its glowing surface. This means the Sun itself travels in a small, steady circle around a point in empty space, pulled through that loop by Jupiter once every 12 years. Jupiter is the only planet massive enough to move the Sun that far. Somewhere far away, an astronomer around another star could watch our Sun wobble and know, without ever seeing it, that a giant lives here. The Sun answers to nothing in its own system except, in this one small motion, to Jupiter. So this is the standing of the world we are approaching. It is the largest planet, the heaviest planet, and the fastest turning planet. It outweighs everything else in the Sun's keeping combined. It flattens itself with its own spin, holds its possessions with 5 times Earth's escape price, and tugs its own star through a slow circle in the dark. And every one of those facts, remember, belongs to the serene, cream-colored light that has decorated the evening sky through the whole of human history. Nothing about that light warns you. The warning only appears when you measure. In the parts ahead, we will take the measurements one system at a time, and we will do it without hurry, because Jupiter rewards patience and punishes nothing at this distance. We will see why this planet came within one threshold of becoming a second sun, and what that near miss would have meant for Earth. We will fall, carefully and only in imagination, down through clouds that never end, into an ocean of metal deeper than worlds. We will watch storms that have outlived every human institution and trace an invisible field that would dwarf the full moon in our sky if our eyes could see it. We will enter, briefly, the most lethal region of space in the sun's whole territory, and meet the armored machines we send there to be slowly ruined. We will visit the 4 great moons that live inside that region, each paying its own price for proximity. And we will step back, at the end, to watch Jupiter shape the solar system itself, scattering some worlds and sparing others, catching comets and pulling them apart, deciding more than any planet should be able to decide. The accounting will be honest, and some of it will carry real weight. But all of it belongs to a world that has behaved this way, steadily and without malice, since long before anything lived. There is nothing here that needs to be feared tonight. There is only a great deal that deserves to be understood, and understanding at this hour can be done with your eyes closed. To understand what Jupiter is, it helps to understand what Jupiter almost became. The recipe is the place to start. Jupiter is made almost entirely of hydrogen and helium, the 2 lightest and oldest elements in the universe. Roughly 9 of every 10 atoms in the planet are hydrogen, and most of the rest are helium, with only a thin seasoning of everything else. That is not the recipe of a rocky world like Earth, which is built from iron and oxygen and silicon, the heavy ash of ancient stars. It is the recipe of the Sun itself. Jupiter and the Sun are made of the same ingredients in nearly the same proportions, drawn from the same original cloud of gas. One of them ignited. The other did not. The difference between them was never a matter of substance. It was only ever a matter of amount. The story of how close it came begins with a race. When the solar system was young, the newborn sun sat at the center of an enormous rotating disk of gas and dust, the raw material from which every planet would be assembled. That disk did not last. Within a few million years, the young sun's light and wind began sweeping the gas away, clearing the nursery. Any planet that wanted to be made of gas had to gather it before the supply vanished. Jupiter formed fast, faster than any of its neighbors, building a heavy seed of rock and ice and then pulling in gas with an appetite nothing else in the disk could match. By the time the nursery emptied, Jupiter had claimed the lion's share of everything that remained. Saturn gathered what was left. Uranus and Neptune, forming more slowly in the colder dark, arrived at the table late and took mostly ice. Even among giants, the shares were unequal. Saturn, Uranus, and Neptune together, all 3 of them combined, hold well under half the mass of Jupiter alone. There was one great winner in the race for the Sun's leftovers, and it has never been challenged since. Winning the race was only half the achievement. Keeping the winnings was the other half. Hydrogen is the lightest of all gases, and light gases escape. Earth cannot hold hydrogen at all. Any of it released into our air drifts upward and, atom by atom, leaks away into space, because Earth's gravity is simply too weak to keep something so quick and so light. Jupiter's gravity is another matter. With an escape price of nearly 60 kilometers per second, not even hydrogen can leave. Every breath of gas the young planet gathered 4.5 billion years ago is still there. Jupiter has spent the whole age of the solar system losing essentially nothing, a vault that has never once been opened. And yet, For all that success, Jupiter stopped short of the one threshold that mattered most. Deep in the core of every true star, hydrogen atoms are pressed together until they fuse, releasing the light that makes a star a star. Fusion needs crushing pressure and ferocious temperature, and those come only from mass. There is a line, and the line is fairly well understood. If a ball of hydrogen gathers roughly 80 times the mass of Jupiter, its core ignites, and it begins to shine by its own fire. Jupiter reached 1/80th of stardom and no further. It is worth being honest about what that number means. 80 times is not a near miss in the everyday sense. But Jupiter was never hours away from ignition. But in a galaxy where hydrogen balls come in every size, from wisps to monsters, our largest planet sits on the same shelf as the smallest stars, built from the same material, shaped by the same physics, separated from them by nothing but quantity. Astronomers sometimes call Jupiter a failed star. The phrase is unkind, but it is not wrong. There is a second, dimmer threshold between planet and star, and Jupiter falls short of that one too. Objects with about 13 times Jupiter's mass can briefly burn a rare form of hydrogen called deuterium. These are the brown dwarfs, the in-between objects, too heavy to be planets and too light to shine steadily. They glow a dull ember red for a while, and then spend eternity cooling. Jupiter sits below even that modest club. It is, by every measure, a planet. But it is the largest kind of planet that nature makes, and it presses against the ceiling of what a planet is allowed to be. That ceiling is one of the strangest facts in planetary science, and it deserves a moment of quiet attention. You might expect that adding mass to a planet would always make it bigger. For rocky worlds it does. But for a giant made of hydrogen, there comes a point where the rule bends and then reverses. Hydrogen compresses. Pile more gas onto Jupiter, and the added weight squeezes the interior more tightly, packing the same material into less space. Beyond a certain point, adding mass makes a hydrogen world no larger at all, and eventually begins to make it smaller. Jupiter sits almost exactly at that turning point. It is very nearly the largest that a cold ball of hydrogen can ever be. You could pour 2 more Jupiters into it, and the planet would grow heavier, denser, and hotter, but scarcely any wider. In a meaningful sense, Jupiter is not just the biggest planet we have. It is close to the biggest planet there can be. Now consider, gently, the road not taken. Suppose the young Jupiter had won its race even more decisively. Suppose it had gathered 80 times more gas before the nursery closed, and the fire had caught in its core. The Sun would have had a companion. Our solar system would have been born a binary system, 2 suns circling one another, which is not an exotic fate. Nearly half the star systems in our galaxy are built that way. But a second sun is not a small change for the worlds nearby. A companion star where Jupiter stands would have flooded the outer solar system with light and stirred the orbits of everything around it. Planets in binary systems can survive, but their paths are pulled and warped by 2 masters instead of 1. The calm, nearly circular orbit that Earth has enjoyed for 4.5 billion years, the steadiness that let oceans persist and life take its unhurried time, was never guaranteed. In many of the alternate versions of our system, Earth's orbit is stretched or unstable, or the planet is never assembled at all. When you look at Jupiter tonight, you are looking at a fire that did not start. The quiet of the night sky, 1 sun and 1 only, is part of what its failure purchased for us. But do not imagine that the fire is entirely out. Here is one of the loveliest and least known facts about Jupiter. It still makes its own heat. Measure the sunlight falling on Jupiter, and then measure the energy Jupiter sends back out into space, and the numbers refuse to balance. The planet radiates significantly more energy than it receives. Something inside is still generating warmth, and the sources are known. Part of it is simply leftover heat from formation, the violence of assembly still leaking away after 4.5 billion years, because a body that large cools very, very slowly. And part of it comes from an ongoing, almost imperceptible collapse. Jupiter is still contracting under its own weight, shrinking by roughly 2 centimeters every year. As it settles, gravitational energy is converted steadily into heat. 2 centimeters a year is nothing on a human timescale. Across the planet's lifetime, that patient settling has released more energy than we can sensibly picture, and it is one reason the interior remains hotter than the surface of the Sun. Jupiter never ignited, but it has never entirely finished forming either. It glows, faintly and in the infrared, with the warmth of its own unfinished collapse. So this is the creature's origin. It was assembled from the Sun's own ingredients. In a hurried race it won without effort. It stopped one threshold short of shining, and in stopping, it left the sky dark enough and the orbits calm enough for a small blue world to keep its oceans. It presses against the physical ceiling of planethood, as large as its kind can be, and it still runs a slow fire of its own making beneath the clouds. Everything dangerous that we will meet in the coming hour, the pressure, the storms, the great magnetic engine, the lethal glow of its radiation, every one of them is a consequence of the simple, patient fact of that mass. Danger, for Jupiter, was never an intention. It is just what that much matter does when it is left alone in the dark with its own weight. And with that understood, we can begin our descent. Every world we know from experience has a flaw. Earth has its ground, the moon has its dust, and even the deepest ocean ends on stone. Jupiter breaks that assumption, and it breaks it completely. There is no surface anywhere on the planet. This is not a poetic exaggeration. It is the plain physical situation. There is no depth at which a falling object would strike ground, no boundary where atmosphere ends and land begins, no floor at the bottom of the clouds. If you could pour water onto Jupiter, there would be nowhere for it to pool. If you could drop a stone into it, the stone would simply keep going. The atmosphere thickens, warms, and brightens with depth, gradually, until the gas has become something that no longer resembles gas at all, and at no point along the way does anything like a landing ever become possible. Jupiter cannot be landed on. It can only be entered, and entering it is a one-way journey. So let us make that journey the only safe way it can be made, in imagination, falling slowly and attending to what the instruments would say. The fall begins in cold. At the visible cloud tops, the temperature sits near -145 degrees Celsius, and the pressure is thinner than the air at Earth's surface. The first decks we pass through are clouds of ammonia ice, the bright ceilings we see from space. Below them come clouds of a compound of ammonia and sulfur, and below those, decks of ordinary water cloud, darker and deeper. Within the first 100 kilometers or so, the pressure around us passes what a person feels standing at sea level on Earth, and it keeps climbing without pause. The light dims. The cold begins, slowly, to give way to warmth, and then to heat, because on Jupiter, depth always means heat. We know this first stretch of the fall not only from theory, but from testimony. One machine has made this descent for real. A small armored probe once entered Jupiter's atmosphere and fell, by parachute, through the brightening dark, reporting everything it felt for as long as it could. It lasted a little under an hour. In that hour, it reached a depth where the pressure was about 22 times Earth's sea level pressure, and the temperature had climbed past 150 degrees Celsius. Then the heat silenced its transmitters, and the planet took it. Here is the number worth holding. At the moment its voice failed, that probe had traveled a fraction of 1% of the distance to Jupiter's center. Everything below that point, all the rest of the world, more than 99% of the way down, no instrument has ever touched. What we know of it, we know from physics, from the planet's measured gravity, and from careful laboratory work with hydrogen under pressure. The deep interior of the nearest giant planet is, in the most literal sense, a place we have only ever calculated. The calculations tell a remarkable story. As we continue falling, the hydrogen around us thickens steadily, from gas towards something denser. You might expect a moment of arrival, a splash, the surface of some great hidden ocean. It never comes. At the pressures we are now passing through, tens of thousands of times Earth's atmosphere, the distinction between gas and liquid quietly stops existing. The hydrogen is compressed into a state that is neither and both, a dense, hot fluid that physicists call supercritical. There is no boundary to cross, no surface tension, no line. Somewhere in the fall, you would realize the substance around you had become more like a liquid than a sky, and you would be unable to say when the change happened. Jupiter does not have an ocean with a shore. It has an atmosphere that becomes an ocean by degrees, seamlessly, over thousands of kilometers. The darkness of the fall, by the way, does not last the whole way down. Sunlight fails within the first few hundred kilometers, absorbed and scattered by the thickening decks, and for a long stretch the descent is black. But heat makes its own light. As the temperature climbs into the thousands of degrees, the fluid around us begins to glow, first a dim red, then orange, then the white heat of a furnace. The deep interior of Jupiter is not dark at all. It is radiant, lit from within by its own compression, a hidden brightness that no sunlight has ever reached and no observer will ever see. Deeper still, at roughly a quarter of the way to the center, the pressure approaches 1,000,000 times Earth's atmosphere, and the temperature nears 10,000 degrees. Here, hydrogen undergoes one of the strangest transformations known to science. The pressure becomes so intense that hydrogen molecules are crushed apart, and then the atoms themselves give up their grip on their electrons. The electrons are squeezed free, left to flow wherever they will, and the hydrogen begins to behave like something wholly unfamiliar. It becomes a liquid metal. It shines. It conducts electricity the way copper does. On Earth, laboratories have produced tiny flickers of this state for fractions of a second, using shock waves and enormous machines, and the achievement is considered heroic. Inside Jupiter, liquid metallic hydrogen simply sits there, in bulk, in a layer deeper than several Earths, stacked end to end, and it has sat there, stable and glowing, for over 4 billion years. Most of Jupiter, by volume, is this single substance. It is the largest ocean in the solar system, an ocean of shining metal, hotter than the surface of the sun, and no eye will ever see it. Hold on to this layer as we pass through it, because it matters later. That conducting, flowing, spinning ocean of metal is the engine of nearly every danger Jupiter projects into space. When we meet the planet's magnetic field, and the radiation that field breeds, we will be meeting the work of this hidden sea. Within that metal ocean, other strange weather falls. Helium, the planet's second ingredient, does not always stay mixed with hydrogen at these depths. In certain layers it separates, gathering into droplets, and the droplets, heavier than what surrounds them, fall. Somewhere beneath us, it is raining helium, a slow, dense rain descending through liquid metal, releasing heat as it falls, and it has been raining that way for eons. It is one reason Jupiter's upper layers carry slightly less helium than the Sun's proportions would predict. The rain is still falling as you listen tonight. And then, at last, the center, the place every falling stone would strive toward and never reach intact. For a long time, the expectation was simple. A world like Jupiter should keep a compact, solid core at its heart, a ball of rock and ice perhaps 10 or more times the mass of Earth, the original seed around which all the gas was gathered. The truth appears to be stranger. When a spacecraft finally mapped Jupiter's gravity field precisely enough to weigh its insides, the core it found was not compact. The heavy material is there, roughly the expected amount, but it is smeared, spread through the inner half of the planet, diluted into the metallic hydrogen around it, like sugar stirred into tea and never fully dissolved. Planetary scientists call it a fuzzy core, and its existence needs explaining. One leading idea is dramatic. Very early in its life, Jupiter may have been struck head-on by another forming world, a body of roughly 10 Earth masses, a planet in its own right. The collision would have shattered the young core and stirred it into the deep interior, and the calculations suggest that even billions of years are not long enough for the mixture to fully settle back out. If that idea is correct, then the giant did not merely outgrow its rivals. It absorbed at least one of them, whole, and carries the remains diffused through its heart to this day. Conditions at the center defy easy description, but the numbers can at least be said aloud. The pressure there reaches tens of millions of times Earth's atmosphere. For comparison, the pressure at the bottom of Earth's deepest ocean trench, a place that crushes submarines, is about 1,100 times our atmosphere. Jupiter's heart exceeds that by a factor of tens of thousands. The temperature is several times hotter than the surface of the Sun, and one final image completes the descent. Suppose you dropped an indestructible object into Jupiter, something no heat or pressure could destroy. It would not fall forever, and it would not land. It would sink until it reached the depth where its density matched the fluid around it, and there it would stop, suspended, floating in glowing metal, entombed in perfect stillness for the remaining life of the solar system. That is what Jupiter offers instead of a surface. Not a flaw, but a fate. There is nowhere in it to stand, nowhere to rest, and nothing to reach. The planet is, from cloud to core, one continuous refusal of solid ground, and everything else we will learn about it tonight stands on that refusal. Rising back up from the interior, we return to the layer of Jupiter that human beings have always been able to see, the clouds. And here we meet the planet's most famous features, the storms. To understand why Jupiter's weather deserves a place in any honest accounting of danger, begin with a question about Earth. Why do our storms die? A hurricane on Earth is an enormous engine, but even the greatest one collapses within weeks. It dies because it runs against friction. It drags its winds across a rough, solid surface. It wanders over cool water or dry land and loses its fuel. And its whole theater of operation, our atmosphere, is a film so thin that the storm has nowhere to grow. Every earthly storm is born with its own ending built in. Now, remove every one of those breaks. Jupiter has no surface, so there is no friction from the ground, ever, anywhere. Its atmosphere is not a thin film, but a layer thousands of kilometers deep. And its fuel does not depend on the fickle warmth of sunlight, because the planet heats itself from below, its interior sending warmth upward steadily, like a stove that is never turned off, under a pot the size of 1,000 worlds. On Jupiter, a storm that gets itself organized faces almost nothing that would ever make it stop. And so Jupiter's storms do not merely grow large, they grow old. On this planet, weather can outlive the civilization that observes it. The proof is the Great Red Spot. It is an anticyclone, an enormous high-pressure storm turning counterclockwise in the southern hemisphere, and it has been watched, more or less continuously, for on the order of 2 centuries. Older telescope records suggest a great storm in the same region far earlier, and if those records describe the same feature, the spot may be 4 centuries old or more. Consider what that span means. This single storm was already turning when the earliest telescopes were pointed at the sky. It was turning through every war, every discovery, and every quiet, ordinary evening of modern human history. Nations have formed, flourished, and dissolved during one storm on Jupiter, and the storm has simply continued, indifferent to all of it. Its dimensions are difficult to hold in the mind. Today, the Great Red Spot is somewhat wider than the entire Earth. And today's storm is the reduced version. Within living memory, it was large enough to hold 2 or 3 Earths side by side, and it has been shrinking for decades, growing rounder as it contracts, for reasons that are not fully understood. Around its rim, winds blow at more than 400 kilometers per hour, well beyond the strongest gusts ever measured on Earth. Yet at its center, like the eye of a hurricane, the air is nearly calm, a still chamber wider than continents, wrapped in a wall of wind. The storm's cloud tops bulge upward above the surrounding decks, and its base runs warm, drawing power from the heat below. And it is not a shallow feature painted on the clouds. Soundings show its roots reaching at least 300 to 500 kilometers down, dozens of times deeper than Earth's entire weather system. The oval we see is only the top of a column, an engine sunk deep into the planet. No one can say when it will die. Smaller storms have been watched drifting into its grip, colliding with the rim, and being absorbed, their energy folded into the larger turning. The spot, in its slow way, feeds. Around it, the whole visible planet is in motion. Those stripes that make Jupiter recognizable in every photograph are lanes of rising and sinking gas, combed into perfect parallel bands by the 10-hour spin. The bright zones are updrafts, air rising and freezing into high white ammonia cloud. The dark belts are the return flow, gas sinking and clearing to reveal the warmer, browner decks below. And along every boundary between them run the jet streams, rivers of wind that circle the entire planet. Earth has a few jet streams, wandering and mild. Jupiter has more than a dozen in each hemisphere, locked in place, alternating direction, blowing eastward, then westward, then eastward again as you move from equator to pole. Several of them run at 500 to 600 kilometers per hour, and they do not gust or rest. They have held their speeds and their positions for as long as they have been measured. On Jupiter, the wind is not an event. It is a permanent feature of the architecture, as fixed as a mountain range. For a long time, no one knew how deep those winds reached. The answer arrived when a spacecraft measured the planet's gravity field precisely enough to feel the mass of the moving air. The jets extend roughly 3,000 kilometers down. Only there, where the thickening fluid begins to conduct electricity and the magnetic field can grip it, are the winds finally forced into lockstep with the deep interior's rotation. Do the arithmetic on that layer, and the result is remarkable. Jupiter's weather system, just the moving, storming, visible part of the atmosphere, contains about 1% of the planet's total mass. 1% of Jupiter is 3 times the mass of the entire Earth. The weather alone, on this world, outweighs 3 Earths. The poles hold the strangest arrangement of all. When spacecraft finally saw Jupiter's poles clearly, they found the storms there organized in a way never observed anywhere else. At the North Pole, a single great cyclone sits at the exact center, surrounded by a ring of 8 more, each the size of a continent, arranged with almost geometric regularity. At the South Pole, a matching pattern, a central cyclone ringed by 5 companions, which later admitted a 6th. On any other world, storms that close together would be expected to merge or scatter. Jupiter's polar rings have held their formation for years, turning like fixed ornaments, and the reason for their stability is still being worked out. It is one more reminder that this planet's atmosphere follows rules we have not finished learning. And through all of it, the lightning. Jovian thunderstorms flash like Earth's, but at another scale. Some strokes rival or exceed the most powerful ever recorded on our world. Strangely, Jupiter's lightning gathers not at the equator, as Earth's does, but toward the poles. Stranger still, flashes have been seen at altitudes too cold for liquid water, which ordinary lightning requires. The explanation appears to be ammonia, acting as an antifreeze, keeping droplets liquid where pure water would be stone-hard ice. Those same violent updrafts are believed to forge one of the strangest forms of precipitation known anywhere, slushy hailstones of ammonia and water that planetary scientists call mushballs, which are hurled upward, frozen, and then fall hundreds of kilometers into the deep atmosphere before evaporating, carrying their chemistry far below the clouds. The bands themselves are not entirely constant. Occasionally, an entire belt fades to white, and for months, the planet looks visibly altered. Then, without warning, dark plumes punch through, and a wave of disturbance travels around the whole world in a matter of weeks, restoring the missing stripe. These global upheavals are among the largest weather events ever witnessed anywhere, and the smaller storm families have their own long lives. 3 white oval storms in one southern band were tracked for decades before they slowly merged into a single storm, which then, to the surprise of nearly everyone, turned red, becoming a second red spot roughly half the size of the first. Elongated brown cyclones drift like dark barges. A chain of white ovals rides another band in a formation observers call a string of pearls. Downstream of the Great Red Spot trails a turbulent wake, one of the most chaotic regions on the visible planet, where eddies are constantly spawned, sheared apart, and folded back into the flow. And near the day-night line, where low sunlight throws long shadows, images have caught thunderheads towering dozens of kilometers above the surrounding cloud deck, convective towers taller than anything Earth's atmosphere could hold upright. One mystery deserves honest mention before we move on. After centuries of observation, no one is certain what makes the Great Red Spot red. The candidate ingredients are known, compounds of sulfur or phosphorus or ammonia chemistry worked over by sunlight, but the question is genuinely unsettled. The most photographed storm in the solar system keeps the simplest fact about itself, its color, unexplained. Set this whole restless machine beside the machines we build, and the danger becomes plain. Any probe descending anywhere on Jupiter falls through wind shear measured in hundreds of kilometers per hour, through hail of ammonia slush, past lightning of extraordinary power, into pressure that has no bottom. And it falls through weather that was already old when its builders were born. The one probe that made the descent fell through storms older than the nation that launched it. On Jupiter, the weather does not happen to the world. The weather is the world, and it does not pause for visitors. Everything we have described so far can, at least, be seen. The storms are painted on the visible face of the planet, and the interior can be drawn in careful diagrams. But Jupiter's largest feature, the largest single structure in the entire solar system apart from the Sun's own sphere of influence, is completely invisible. It is the planet's magnetic field, and it is the place where Jupiter stops being merely extreme and becomes, in a quiet way, imperial. The engine of that field is the metal ocean we crossed on the way down. A magnetic field like Jupiter's requires 3 things: a fluid that conducts electricity, motion within that fluid, and rotation to organize the motion. Jupiter has all three in unmatched supply. Its liquid metallic hydrogen conducts like copper. Heat rising from the deep interior keeps that entire conducting ocean churning. And the 10-hour spin winds those churning currents into immense, ordered spirals. The result is a dynamo, a natural generator of planetary scale, running continuously for over 4 billion years. Earth runs a dynamo too, in its molten iron core, and Earth's version gives us the field that guides our compasses. Jupiter's version is fed by an ocean of conducting metal thousands of times larger, spun more than twice as fast. Summed over its whole volume, the field it produces holds roughly 20,000 times the energy of Earth's. At the cloud tops, the field is 10 to 20 times stronger than the field at Earth's surface. This is, by an enormous margin, the strongest planetary magnetic field the Sun possesses. Now consider the size of the region that field controls. Around every magnetized planet, there is a bubble, a volume of space where the planet's field, rather than the Sun's wind, is in command. That bubble is called a magnetosphere. Earth's is a modest teardrop, sunward edge standing about 10 Earth radii upstream. Jupiter's magnetosphere is a country of another order. On the sunward side, the boundary where the solar wind is finally stopped stands millions of kilometers upstream of the planet. The bubble as a whole is wider than the Sun itself. If Jupiter's magnetosphere glowed in some color our eyes could register, it would hang in Earth's night sky as an oval 2 to 3 times the width of the full moon. There would be the moon, and near it, this larger, stranger bloom of light surrounding a bright point, and every person who ever lived would have grown up knowing that the sky's largest object belonged to Jupiter. The structure is there tonight, exactly that large. We simply cannot see it. Downwind, the story becomes almost implausible. Like every magnetosphere, Jupiter's is blown into a long tail by the passing solar wind, streaming away from the Sun like a windsock. Jupiter's magnetotail is the longest structure in the solar system. It stretches away for a distance comparable to the entire span between Jupiter's orbit and Saturn's orbit. When the two planets fall into the right alignment, Saturn, itself a giant with a great field of its own, passes through the wake of Jupiter's. One planet's magnetic weather reaches the next planet out. Nothing else in the Sun's family projects influence across interplanetary distances that way. The field's fine structure carries its own surprises. It is tilted about 10 degrees from the planet's spin axis, so as Jupiter turns, the whole field nods, sweeping up and down through everything nearby every 10 hours. It is lumpy rather than smooth, stronger in some regions than others, and near the equator sits a concentrated patch of anomalous field, almost like a second isolated pole in the wrong place. That lumpiness is a signature. It tells us the dynamo runs comparatively close beneath the surface layers, not neatly buried at the center, so we are seeing the machinery near the top of the metal ocean, barely smoothed by distance. And because the field is anchored to the planet, the entire magnetosphere, this structure wider than the Sun, rotates with Jupiter's 10-hour day. Picture that for a moment. A volume of space that would swallow a star, spinning completely around twice in every Earth day, whipping its contents along with it. The fast spin does one more strange thing. It flings the trapped gas outward, stretching the field lines near the equator into a flattened, spinning sheet, the way dough spreads when a baker spins it. Earth's slower, lighter magnetosphere never develops anything like it. The 10-degree tilt has a consequence worth noticing for later. Because the field nods as the planet spins, the flattened sheet of trapped plasma sweeps up and down across the orbits of the moons, passing over each of them twice in every 10-hour rotation. A moon of Jupiter does not experience a steady rain of radiation. It experiences a tide of it, rising and falling on a 10-hour rhythm as the plasma sheet flaps past like a slow wing. The moons live inside a pulse. They have lived inside it for 4 billion years. Remarkably, human beings discovered this empire before any spacecraft went there, because Jupiter is loud. The spinning field and the charged particles caught in it together make Jupiter the most powerful planetary radio source in the sky. Its radio bursts were first picked up by ground-based antennas generations ago, arriving as steady hisses and sudden roars, and at certain wavelengths Jupiter's bursts can rival the radio output of the Sun itself. If your eyes were tuned to radio light, Jupiter would be one of the brightest objects in the night sky, a lighthouse turning every 10 hours. Part of that glow comes from electrons moving near the speed of light, spiraling along the field lines and radiating as they turn. Long before anyone could travel there, the radio sky was already reporting that something around Jupiter was accelerating particles to extraordinary energies. Where do those particles come from? Here the system reveals its most elegant and most ominous piece of engineering. The magnetosphere is not primarily filled with solar wind, the way Earth's is. It is filled from inside. Its innermost large moon, a volcanic world we will visit properly in a later part, erupts constantly, and Jupiter's field sweeps up the escaping gas, roughly a ton of it every second. Sulfur and oxygen, stripped into charged fragments, spread into a donut of glowing plasma wrapped around the planet along the moon's orbit. Then the great field grips that plasma and spins it up, faster and faster, accelerating it as it whips around with the 10-hour rotation. Jupiter's radiation, in other words, is largely homegrown. The planet manufactures its own ammunition, using a moon as the factory and its spin as the engine. Immense electrical currents close the circuit, millions of amperes flowing along the field lines, connecting the moon to the planet's poles in a permanent, invisible wiring. You can see the receipts of all this at the poles. Jupiter's auroras are the most powerful in the solar system, glowing rings around each magnetic pole that radiate hundreds of times more energy than Earth's northern lights. And they are permanent. Earth's auroras come and go with solar storms, gifts of a restless sun. Jupiter's are powered from within by the planet's own rotation and its own moon's breath, so they burn continuously, day and night, year upon year. Within those glowing rings, careful images reveal something almost intimate. Distinct bright spots, each trailing a little tail of light, mark the exact places where magnetic field lines from the great moons touch the atmosphere. The moons write their signatures in Jupiter's polar light, each one a moving pinpoint of aurora, tracing its orbit on the planet's sky. The closest moon signs continuously. The others add their marks. It would be, if we could stand beneath it, among the most beautiful sights in the solar system. And here is the turn, the place where beauty and menace exchange places. On Earth, our magnetic field is a shield. It stands between life and the solar wind, deflecting charged particles, quietly protecting every living thing beneath it. It is one reason our world has stayed habitable. Jupiter's field, 20,000 times stronger, does not behave like a shield. It behaves like a trap. It does hold the solar wind at a great distance, but inside the boundary, it gathers charged particles, holds them, and accelerates them, generation after generation, until the space around the planet is more hostile than the raw solar wind could ever be on its own. The very mechanism that protects Earth, scaled up to Jupiter's size and spin, becomes a weapon pointed in every direction at once. The shield became the sword. What that sword actually does, to flesh and to machines, is the subject we take up next, gently and from a very safe distance. We come now to the heart of Jupiter's reputation, the thing that makes it, in practical terms, the most dangerous destination in the solar system. It is not the pressure, which at least announces itself. It is not the storms, which can be seen and charted. It is the radiation, which cannot be seen, cannot be heard, and cannot be felt until the harm is already done. This part of the accounting deserves to be taken slowly, because it is the part that has shaped every journey we have ever made to the giant, and every journey we will ever make. The mechanism first, calmly. We have seen that Jupiter's magnetic field traps charged particles, electrons and protons, and heavier ions, most of them fed into the system by the volcanic innermost moon. We have seen that the field spins with the planet, whipping that trapped material around every 10 hours and accelerating it, pass after pass, year after year. There is no friction in space to slow the particles down, and the field does not let them leave. So they accumulate, and they speed up. The most energetic electrons around Jupiter travel at very nearly the speed of light. Wrapped around the planet, thickest near the magnetic equator, these swarms of fast particles form the radiation belts, invisible rings of the fastest matter in the solar system, nested one inside another like the layers of an onion. Earth has radiation belts too, discovered at the very dawn of the space age, and ours are dangerous enough that spacecraft designers treat them with respect. Jupiter's belts carry particle intensities thousands of times greater, at energies far higher. Between the two there is no comparison, only a shared name. What would that environment do to a person? The numbers exist, and they are worth hearing slowly. Radiation dose is measured in units called sieverts. A chest X-ray delivers about 1/10,000th of a sievert. A dose of 1 sievert, received quickly, causes radiation sickness. A dose of several sieverts, received quickly, is commonly fatal. Near the orbit of the innermost large moon, deep inside the belts, the ambient radiation delivers on the order of 36 sieverts per day. Run the arithmetic, and it comes out plainly. An unprotected human being in that region would absorb a lethal dose, not in months, not in weeks, and not in days, but in minutes, to at most a few hours. And this would not be the slow statistical harm of a slightly elevated cancer risk. It would be prompt radiation sickness, the failure of the body's fastest renewing tissues, unfolding on the timescale of a single shift at work. Farther out, at the ice moon with the hidden ocean, the surface still receives several sieverts per day, a lethal accumulation inside 2 days of standing on the ice. These are, by an enormous margin, the most hostile radiation environments anywhere in the solar system, outside the immediate vicinity of the Sun. Machines do not bleed, but they fail in ways that rhyme. A modern spacecraft is a lattice of fine electronics, and to fast-charged particles, that lattice is a target. A single energetic particle punching through a memory chip can flip a stored bit, turning a 1 into a 0, and quietly corrupt a command. Enough strikes, and processors reset, instruments stutter, and the craft drops into protective safe modes, curling up like a startled animal. Star trackers, the delicate cameras a spacecraft uses to find its orientation by the stars, are blinded by flashes as particles strike their sensors, filling their images with false stars. Solar panels degrade with every pass through the belts, their crystalline cells bruised at the atomic level, their power output stepping permanently downward. Camera detectors accumulate speckled damage, as if the film were being slowly fogged. Lenses and glass darken under the accumulating dose. Unhardened commercial electronics, the kind in an ordinary phone, would accumulate fatal damage near Jupiter within days. Even the toughened, radiation-hardened components built for deep space have their limits. And near Jupiter, Engineers speak of a spacecraft's total accumulated dose the way physicians speak of a patient's exposure, as a budget that is spent one encounter at a time and can never be recovered. There is also a subtler failure mode, stranger than simple damage. A spacecraft moving through that sea of charged particles collects charge the way a wool sweater does on a dry day. Different surfaces charge at different rates, and voltages can build to thousands of volts between one part of the craft and another, until the difference discharges in a spark. A spark inside a machine packed with delicate electronics is a small lightning strike in the worst possible place. Some anomalies at Jupiter are believed to be exactly this: the spacecraft stung from within by electricity it gathered simply by being there. We learned most of this the hard way, from the very first machine ever sent. Before any spacecraft had made the journey, mission planners feared two obstacles. The first was the asteroid belt, which on the maps of the day looked like a wall of tumbling stone between the inner and outer solar system. The second was Jupiter's radiation, whose radio glow had been measured from Earth but whose true intensity no one knew. The asteroid belt turned out to be a mercy. It is, in truth, almost entirely empty space, and the first crossing was made without incident, as every crossing since has been. The radiation was the opposite story. It was far worse than the estimates. As that first small probe swung low over the cloud tops, its instruments counted a dose accumulating at a rate no one had planned for. In the space of hours, the craft absorbed several hundred times the radiation dose that would kill a human being. False commands were triggered inside its electronics. Images arrived, streaked, and darkened. A few instruments were left permanently scarred. The probe survived, but narrowly, and its builders understood that the margin had been luck as much as design. Its twin, following behind, was quietly retargeted to pass at a safer distance. Those two crossings, one bruising and one cautious, set the terms that have governed every visit since. Jupiter's proximity is purchased in radiation, and the price is not negotiable. Even armor, it turns out, is complicated at Jupiter. The obvious response to radiation is shielding, and shielding does help, but the physics plays a quiet trick. When a very fast electron slams into dense metal, it stops, and in stopping it sprays out X-rays, a secondary radiation born inside the shield itself. Thicken the armor carelessly, and you can make the interior worse, trading the original particles for a wash of X-rays of your own manufacture. Designing a radiation vault for Jupiter is therefore a specialized art, a balance of materials and thicknesses, and not a simple matter of adding metal until the problem goes away. Against Jupiter, even hiding must be done with skill. And the belts, it should be said, are not perfectly constant. They breathe. Their supply line is the volcanic moon, and when its eruptions surge, the whole magnetosphere is measurably reloaded with fresh plasma, brightening the system's radio glow and thickening the invisible rain. The radiation around Jupiter has weather of its own, a slow inhale and exhale that follows the moods of a moon. One more feature completes the picture, and it explains something we will rely on later. The belts are not spread evenly around the planet. They hug the magnetic equator, where the trapped particles bounce and drift in their thickest crowds. Toward the poles, beneath the inner edge of the belts, there runs a comparatively quieter corridor, a gap in the fortifications. A spacecraft that approaches over the top of the planet, diving down across the pole and skimming past at low altitude, can thread that corridor, spending minutes rather than hours in the worst zones. Remember that gap. It is the single geometric mercy in the whole system, and, as we will see in the next part, an entire mission was designed around it, the way a climber designs a route around a single ledge on a cliff face. Step back then, and take in the whole of what we have described, because it changes the meaning of the maps. In the atlas of the solar system, the space around Jupiter looks open, a wide black emptiness, dotted with moons, seemingly free for the traveling. It is not open. Draw the radiation onto the map, and the inner Jovian system fills in with a zone that is, for human beings, permanently closed, a region that our species can send armored machines into, but will never enter in person, not with any technology now imagined. Every plan ever drawn for human presence around Jupiter places the crews far out, at the outermost of the great moons or beyond, with the interior left to the robots. The belts do not rage. They do not gust or storm or choose. They simply persist, humming at the same lethal intensity through every human century, a fixed feature of the Sun's family, as permanent as the planet's spin. The universe wrote a keep-out notice around its largest planet, in ink we cannot see, and we have learned, carefully and at some cost, to read it. Knowing all of this, you might reasonably ask why we go at all. And yet we do go. Spacecraft are circling Jupiter as you listen tonight. The story of how they survive there and of what survival costs is one of the quietly heroic chapters of engineering, and it reads less like exploration and more like a siege. In this part, we look at the craft of visiting a place that damages everything that visits, because the shape of these machines and the shapes of their orbits are Jupiter's dangers made visible. Every design choice is a portrait of the threat it answers. Begin with the most famous piece of Jovian armor, the Volt. The spacecraft that now flies closest to Jupiter carries its command electronics, its computer, its power controls, the whole of its thinking machinery, sealed inside a box of titanium. The walls are about a centimeter thick, and the box in total has a mass of roughly 200 kilograms. 200 kilograms is a substantial fraction of everything the mission could carry across interplanetary space, spent not on instruments, not on fuel, not on antennas, but on a strongbox whose entire purpose is to slow down radiation. And slow it is the honest verb. The Volt does not stop Jupiter's radiation. Nothing practical could. The most energetic particles pass through titanium as if through fog. What the Volt does is thin the rain, cutting the dose accumulating inside to a fraction of the dose outside, so that the electronics age at a survivable rate. The designer's own language is telling. They speak of the mission's lifetime not in years but in accumulated dose, a fixed budget of harm the craft can absorb before its mind begins to fail. Every close pass spends some of that budget. Nothing earns it back. A spacecraft at Jupiter is, from the day it arrives, dying on a schedule, and the whole art of the mission is to arrange that the science is finished before the dying is. The orbit is the second piece of armor, and it may be the more elegant one. Remember the gap in the fortifications, the comparatively quiet corridor that runs beneath the inner edge of the radiation belts, over the poles. The mission was built around that corridor, the way a route is built around the one safe ledge on a cliff. Its orbit is a long, narrow ellipse. For days at a stretch, the spacecraft keeps far from the planet, out where the radiation is thin, resting, transmitting its findings home, spending almost nothing. Then it falls inward, gathering speed, and makes its approach not from the side, where the belts stand thickest, but from above, diving down across the North Pole, skimming the cloud tops at low altitude, and climbing away past the South Pole, all in a matter of hours. It slips beneath the belts the way a swimmer ducks under a cresting wave. Then it swings far away again to recover. Hours of exposure, purchased with days of retreat. Even so, the accumulating dose is relentless. Instruments are expected to degrade on a known schedule. The camera, a device beloved by the public, was never expected to survive the whole mission, and every image it returns past its projected lifetime is understood by its operators as a gift. There is one more quiet feat folded into that mission, easy to miss beside the vault and the diving orbit. It runs on sunlight. At Jupiter's distance, sunlight arrives at about a 25th of its strength at Earth, and for decades, solar-powered flight out there was considered simply impossible. The mission answered with scale and patience, wings of solar panels the size of a room, built from cells qualified to endure both the deep cold and the steady bruising of radiation, harvesting a faint light most designers had written off. It became the first solar-powered spacecraft ever to operate so far from the Sun. Even the mission's power supply, in other words, is a small act of defiance, wringing a living from a sky that offers almost nothing and takes from everything. That is the newest chapter of the siege. The one before it makes the price even clearer. An earlier spacecraft spent years orbiting Jupiter, the first ever to take up residence, touring the great moons through dozens of encounters. It was built with the best shielding of its day, and its planners budgeted, as all Jupiter planners must, for a fixed lifetime of accumulated dose. The mission was so productive that it was extended, and extended again, and by the end, the craft had absorbed several times the radiation it was designed to withstand. The record of its later years is a diary of wounds. Camera images arrived with anomalies. The onboard recorder that held its precious data stumbled and had to be coaxed and nursed by controllers hundreds of millions of kilometers away. Subsystems tripped into safe mode without warning. Ground teams learned to treat every new glitch with a standing assumption. At Jupiter, the default explanation for any anomaly is radiation, and hardware fault is the second guess. The spacecraft kept working, remarkably, because its builders had left margin everywhere, but it ended its life as a machine visibly worn down by its address, functional the way an old tool is functional, scarred, slowed, and trusted only carefully. And then its builders did something that says more about Jupiter's neighborhood than any measurement could. When the mission's fuel ran low, they did not simply let the old craft drift. They steered it, deliberately, into Jupiter itself. It fell into the atmosphere and vaporized, joining the planet it had studied. The reason was not sentiment. It was contamination. Among the moons that spacecraft had visited was the ice world with the hidden ocean, a place where something might, conceivably, live. A dead, uncontrolled hull, left in orbit for centuries, might one day wander into that moon and strike it, carrying with it whatever hardy earthly microbes had survived the journey inside its structure. The probability was small, but the stakes were judged absolute, and so the machine was destroyed on purpose, cremated in Jupiter's clouds, to guarantee that the ocean would stay untouched. Sit with that for a moment. Around Jupiter, we do not merely armor our machines. We arrange their deaths, carefully, as an act of hygiene toward a sea no one has ever seen. There was also, on that same mission, the small probe we met earlier, the one that made the only deliberate descent into the atmosphere. Its radiation story deserves its place in this ledger too. In the single hour of its fall, before pressure and heat ended its work, it absorbed a dose sometimes described as the equivalent of tens of millions of medical X-rays. It was built for exactly that, an armored messenger with one task and no return, and it completed the task. It remains the only object from Earth ever to enter the body of the giant on purpose, and its atoms are part of Jupiter now, dissolved somewhere in the deep. The newest missions carry the same lessons in new shapes. The ice moon with the ocean is now the object of the most anticipated search for habitability in the solar system, and you might expect the natural plan, put a spacecraft in orbit around that moon and study it at leisure. The radiation forbids it. That moon orbits inside the belts, and a craft parked around it would absorb a fatal dose within weeks to months, far too little time for the science. So the mission was designed as a dodge. The spacecraft orbits Jupiter instead, on long, wide loops that keep it outside the worst zones, and dips inward again and again, dozens of times across its mission, each pass sweeping close to the Moon at speed, gathering data in a matter of hours, and retreating before the dose mounts. Summed across years of flight, its total time deep inside the radiation amounts to only days. It too carries a titanium vault. Its entire architecture, every loop of its trajectory, is a radiation budget drawn as a flight path. A companion mission from another continent takes the complementary path, touring the system before settling, at journey's end, into orbit around the one great moon far enough out and shielded enough to make a long stay survivable. Step back from the details, and the pattern is unmistakable. We visit Jupiter the way divers visit a deep wreck. Briefly, in armor. Watching the gauge the whole time, because the gauge is life and it only runs one way. No other planet imposes terms like these. At Mars we land, rove, linger for decades. At Saturn, a spacecraft circled in comfort for 13 years. At Jupiter, every arrival begins a countdown, every approach is timed to the hour, and every mission ends either in retreat or in deliberate destruction. The machines we send are the finest things we make, and Jupiter wears them out as a matter of course, without effort and without notice. That is what it means, in practice, for a planet to be dangerous. Not that it strikes, but that it costs, steadily, everything that comes near. No world exists alone, and Jupiter least of all. The giant keeps a family, 95 moons known at last count, ranging from captured boulders a few kilometers across to worlds larger than planets. Most are small and far and safe. But the 4 great moons, the ones any small telescope will show you as a neat line of star-like points, live close in, inside or at the edges of everything we have just described. They are extraordinary worlds by any measure, and each of them, examined honestly, is a record of what it costs to orbit a monster. This part is their portrait, drawn not as a tour of destinations, but as a study of what Jupiter does to the things it holds. Begin with the innermost of the 4, the volcanic moon. It is about the size of Earth's own moon, and it is the most volcanically active body known to exist, anywhere. Not modestly more active than Earth. Incomparably more. Its surface carries hundreds of volcanic centers, calderas glowing with exposed lava, eruptive plumes that rise not kilometers but hundreds of kilometers, arcing into space itself in great umbrella-shaped fountains. The moon repaves itself so relentlessly that it has no lasting craters at all. Impacts happen, and the scars are simply buried in fresh volcanic material, again and again, so that the surface you would see today is geologically brand new, younger than almost any landscape in the solar system. Summed together, its heat output runs on the order of 100 trillion watts, and its hotspots reach temperatures higher than any other solid surface known. Here is the part that belongs to our story. None of that heat is the moon's own. A body that size, left alone, would have cooled to stillness billions of years ago, exactly as our own moon did. The furnace is Jupiter. The mechanism is worth understanding because it is gravity behaving in a way we rarely think about, not as a pull, but as a grip that needs. The moon's orbit is not quite circular. It is kept slightly oval by a remarkable arrangement we will come to in a moment, so its distance from Jupiter changes continuously. When it swings nearer, Jupiter's tides stretch it, raising a bulge in the solid rock itself. When it swings away, the rock relaxes. The flexing of the ground amounts to as much as 100 meters of rise and fall, in stone, on every single orbit, and an orbit takes only about 42 hours. Picture the land beneath your feet lifting and settling by the height of a 30-story building, twice a week, forever. Rock that is bent and unbent that way heats up, exactly as a wire bent back and forth grows warm in your hands. Jupiter is kneading the moon like dough, and the moon's volcanoes are simply the heat of that kneading escaping. The entire spectacular violence of the most volcanic world in the solar system is imposed from outside by the giant's grip. And the arrangement that keeps the orbit oval is its own quiet marvel. The three inner great moons are locked in a gravitational rhythm. For every single orbit the outer one makes, the middle one makes exactly 2, and the inner one exactly 4. 1, 2, 4. A resonance that repeats perfectly, so that the moons line up on schedule and tug at one another in the same way, every time, forever preventing the inner orbits from settling into calm circles. The pattern is self-maintaining. The moons continually relock each other into it, which means the tidal engine cannot wind down. The kneading, the flexing, the volcanoes, all of it is powered by an arrangement that renews itself, a machine with no off switch, running since the early days of the solar system. The volcanic moon pays a second tax, one we have already seen from the other side. Its eruptions and the constant scouring of its surface by trapped particles feed material into space, roughly a ton every second, sulfur and oxygen streaming away into Jupiter's magnetic keeping. That material becomes the glowing donut of plasma along the moon's orbit, and that plasma, spun and accelerated by the great field, becomes the radiation belts themselves. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Jupiter heats the moon by force. The heat drives the volcanoes bleed gas into space, and Jupiter forges that gas into the radiation that sterilizes the whole inner system. Jupiter uses one of its own moons as an armory. The moon is both victim and unwilling accomplice, the source of the very environment that makes its neighborhood lethal. Next outward lives the opposite world, the ice moon, and its story is the most bittersweet in the solar system. Beneath a shell of ice a few kilometers to a few tens of kilometers thick lies a global ocean of salt water, kept liquid by the same tidal kneading in a gentler measure. The measurements that revealed it are convincing, and the volume they imply is astonishing. That one moon likely holds more liquid water than all the oceans of Earth combined. Warm, salty, dark, and continuous for 4 billion years, it is, by most reckonings, the most promising place in the solar system to look for a second, independent origin of life. The reddish-brown stains that streak its fractured face are consistent with ocean salts, brought up through cracks and then darkened by radiation, the hidden sea's chemistry written faintly on the ice. There are even indications, still tentative, of plumes venting water vapor into space, which would mean the ocean occasionally exhales, and a passing spacecraft could taste it without ever landing. And yet look where that ocean sits. The moon orbits inside the radiation belts, and its icy face receives several sieverts per day, a lethal dose for a human in under 2 days. An environment that shreds organic molecules and would erase, in short order, the very chemical traces a lander would come looking for. The surface most likely to matter in the search for life is among the most irradiated ground in the solar system. Any probe that lands there must be armored, must work fast, and must likely dig, because only beneath meters of ice would the ocean's chemistry survive the sky. Here is the cruelty of position, stated plainly. The ocean exists because Jupiter needs it warm. The ocean is nearly unreachable because Jupiter guards it with radiation. The same hand warms the water and stands over it. Whatever may or may not drift in that dark sea, it lives in a fortress, and the fortress was built, without intention, by the landlord. Third out is the giant of moons, the largest moon in the solar system, larger than the planet Mercury. It would be a planet in any fair accounting, and it carries a planet's equipment. Alone among all known moons, it generates its own magnetic field, a true internal dynamo running in a molten iron core, wrapping the moon in a small magnetosphere of its own, complete with its own miniature auroras glowing at its poles. It even appears to hide its own salty ocean, deep beneath layers of ice. A moon with a metal heart, a magnetic shield, an ocean, and auroras. And it is still not enough. Its field, strong by lunar standards, is feeble beside the flood it floats in. It carves out only a modest protected bubble, and near its poles, where its own field lines open outward, Jupiter's particles pour down onto the ice unimpeded. The one moon in the solar system that built itself a shield still cannot fully stand behind it. Within Jupiter's dominion, even the well-armored lie exposed. And then there is the outermost of the four, the quiet one, and its testimony may be the most eloquent of all. It orbits far enough out to escape the worst of the radiation, and it never joined the 1-2-4 rhythm of its siblings, so it was never needed, never heated, never resurfaced. It simply endured. Its face is the oldest continuously exposed landscape known, crowded with craters shoulder to shoulder, 4 billion years of impacts with nothing to erase them. Read rightly, that battered face is a ledger. Every mark on it is something Jupiter's gravity pulled inward that found the moon in its way. It is what a world looks like when it stands, unhealed, in the giant's weather. Its siblings hide the damage, one under fresh lava, one under shifting ice. The far moon simply kept the receipts. 4 moons then, and 4 verdicts. One is needed until it burns, and armed against its will. One is warmed into an ocean it is forbidden to share. One built its own defenses and finds them insufficient. And one, spared the grip, wears every blow of 4 billion years. These are among the most wondrous places the solar system has made, and it is right to marvel at them. But seen from tonight's distance, they are also this. They are what live in a monster's house. It is worth adding, softly, that these 4 points of light changed human history. They were the first objects ever seen to orbit something other than Earth, and the sight of them, circling their giant in plain defiance of the old maps, helped teach our species that it was not the center of things. The monster's captives, glimmering in a small telescope, quietly rearranged the human mind. Let us pause here, near the midpoint of our journey, and gather up what we have seen so far, because the pieces are about to assemble into something larger. We began with a serene light in the night sky and measured the world behind it, a planet that outweighs everything else in the sun's family combined. We fell through clouds that never end, into an ocean of liquid metal, and found no floor anywhere. We watched storms that outlived nations, and traced an invisible magnetic country wider than the sun, spun around every 10 hours. We entered, cautiously, the radiation that field breeds, and we met the armored machines we sacrificed to it. And we visited the 4 great moons, each paying its own toll for proximity. Every one of those chapters described what Jupiter is, or what it does to things near it, today. Now the story widens, in space and in time, because Jupiter's gravity has never confined its attention to its own neighborhood. In this part, we ask what the giant has done to the solar system itself, and the answer, assembled from the evidence of orbits, is quietly astonishing. Jupiter helped decide the shape of everything. including the existence and the size of the world you are resting on now. The story begins before the planets were finished, when the young solar system was still a disk of gas and dust, with newborn worlds embedded in it like seeds. A planet embedded in such a disk does not necessarily stay where it formed. It exchanges momentum with the gas around it, and it drifts. The reconstruction most consistent with today's solar system says that the young Jupiter drifted inward, and not slightly. It spiraled in toward the Sun, deep into the region where the rocky planets were assembling, perhaps as far in as the orbit where Mars circles today. Had nothing intervened, it might have continued inward and become one of the close-orbiting giants we now find around other stars. Something intervened. Saturn had formed behind it, and as Saturn grew, the two giants fell into a gravitational partnership, locked in resonance, and the coupled pair reversed course, migrating slowly back outward toward the far orbits they hold today. Inward, a turn, then outward again, like a sailboat tacking against the wind. A single voyage, made once, 4.5 billion years ago. The solar system still wears its wake. Look at the asteroid belt first. Between Mars and Jupiter circles a ring of rubble, millions of bodies, and the old romantic idea was that they were the wreckage of a planet that broke apart. The truth is the opposite, and it is stranger. Weigh the entire belt, every asteroid combined, and the total comes to just a few % of the mass of our moon. That is not the debris of a destroyed planet. It is the leftover material of a planet that was never allowed to form. Planets grow by gentle mergers, small bodies meeting slowly and sticking. Jupiter's gravity, sweeping through and then reaching across that zone, stirred the orbits into a crossfire, tilting and stretching them so that neighbors met at shattering speeds instead of gathering ones. Collisions there broke bodies apart rather than joining them, and enormous quantities of material were flung away entirely, into the Sun or out of the system. The asteroid belt is a construction site where the builder was chased off, the bricks scattered, and nothing ever finished. It has circled, unfinished, for 4 billion years, and the reason has a name. Look next at Mars. There is a long-standing puzzle about the red planet, and it is a puzzle of size. Our models of planet formation, applied to the material that should have orbited in that zone, keep producing a Mars comparable to Earth. The real Mars is about 1/10 of Earth's mass, a small world, and its smallness demands an explanation. The favored one follows directly from the voyage. If young Jupiter swept inward through that region, its gravity would have cleared much of the feeding zone, scattering the material Mars would otherwise have eaten. Mars formed anyway, but it formed hungry, from a starved zone, and it stopped growing early. If that account is right, then Mars is small because Jupiter passed by before Mars could finish. A whole planet's stature, decided by the giant's itinerary. There may be a darker entry in the ledger still. When researchers run the early solar system backward and forward in their models, trying to reproduce today's orbits, many of the reconstructions work distinctly better if one more giant planet was present at the start, a fifth great world alongside Jupiter, Saturn, and the two ice giants. In those versions of history, the era of shuffling that followed the disk's disappearance turned violent, and the extra giant, swung too close to Jupiter, was thrown, by that encounter, out of the solar system entirely, exiled into interstellar space. We cannot confirm that it happened here. But we know, from surveys of the galaxy, that rogue planets exist in great numbers, starless worlds drifting alone through the dark, and we know that gravitational eviction by a system's own Jupiter is one of the natural ways to make them. It is possible, and by some accountings likely, that our solar system once had another giant, and that Jupiter's hand is the reason we count 4 instead of 5. Somewhere out there, in that case, a frozen world without a sun carries the oldest grudge in the solar system. The same voyage may even explain a stranger absence. When we survey planets around other stars, the most common kind we find is a class our system entirely lacks: worlds between Earth and Neptune in size, orbiting close to their suns. They are everywhere, and we have none. One explanation is humbling. If such worlds were forming close to our young sun, Jupiter's inward sweep would have driven them to their destruction, herding that whole first generation of inner planets into the star, before the tack outward left cleared ground on which Mercury, Venus, Earth, and Mars later formed. In that telling, ours is a second draft, written on a page the giant erased, and the most ordinary kind of planet in the galaxy is missing here because Jupiter removed it. Nor did the rearranging end in antiquity. It continues in settled, permanent forms. Locked into Jupiter's own orbit, 60 degrees ahead of it and 60 degrees behind, travel two great swarms of asteroids, trapped at the points where the gravity of sun and planet balance. They lead and trail the giant like an escort, thousands upon thousands of them, and they may collectively rival the main belt in numbers, two invisible crowds that most people have never heard of, holding formation for billions of years. Within the main belt itself, Jupiter's influence is written so plainly you can read it in a simple chart. Plot the orbits of the asteroids, and you find gaps, thin bands of emptiness, at precisely the distances where an asteroid's orbital period would fall into rhythm with Jupiter's, 1/3, 2/5, 1/2 of the giant's period. Any body that drifts into those rhythms gets tugged in the same direction on every lap, its orbit pumped and stretched until it is thrown clear. The gaps are Jupiter's signature, carved into the architecture of the belt, resonance made visible. And one of those rhythms works as a conveyor. Asteroids nudged into it have their orbits stretched until they cross Mars's path, then Earth's. A meaningful fraction of the near-Earth asteroids, the bodies our surveys watch most carefully, were delivered inward by exactly that route. The stones that pass near our world were, many of them, dispatched by Jupiter's arithmetic. Which brings us to the comets, and to a reputation that deserves an honest audit. Every comet that falls in from the deep outer system must run Jupiter's gauntlet, and the giant deals with them as it pleases. Some it slings out of the solar system entirely, never to return. Some it captures, bending their long, wild orbits into short, obedient loops. There is a whole recognized family of comets defined this way, their periods under 20 years, their farthest points clustered near Jupiter's orbit, a population shaped and owned by the planet that tamed them. At least one comet has been watched being temporarily captured into orbit around Jupiter itself, circling the giant for decades before being released back to the sun, caught and let go, like fruit tested and returned. And some comets, inevitably, are handed inward, redirected toward the sun and toward us. Here is the honest accounting. Jupiter is often called Earth's shield, the great vacuum cleaner that eats impactors before they reach us, and it does absorb and eject a great many. But the same gravity also bends fresh comets onto Earth-crossing paths they would never have found alone. Model it carefully, and the answer refuses to be simple. Remove Jupiter, and Earth's impact rate can rise or fall depending on the assumptions. Shield on some nights, dealer on others. What is certain is only this. Jupiter decides trajectories more than any other planet, and Earth lives downstream of its decisions. Even the soft glow of the zodiacal light, that faint cone sometimes visible after sunset, is partly dust ground from comets Jupiter captured, the giant's debris, scattered as far as our own evening sky. Everything we have said about Jupiter's power over comets and asteroids has been, so far, a matter of orbits and inference, gravity read from charts. But once, within living memory, the whole process played out in front of us, from capture to destruction, with every great telescope on Earth watching. It remains the only time human beings have ever witnessed a planetary-scale impact anywhere in the solar system, and Jupiter, fittingly, was both the trap and the target. The story deserves to be told slowly, because nothing else in the modern history of astronomy carries quite its weight. It began, as these stories usually do, unnoticed. A comet fell in from the outer solar system, one of the countless icy wanderers on long elliptical paths, and at some point, decades before anyone knew it existed, it passed close enough to Jupiter to be caught. Not destroyed and not deflected, but captured, swung out of its orbit around the Sun and into an orbit around the planet itself. This alone is a rare fate. Comets belong to the Sun. This one became, for a time, a moon of Jupiter, a dirty snowball a few kilometers wide, looping the giant unseen while human affairs went on below, entirely unaware. The monster had taken a prisoner, and no one on Earth knew. Then came the pass that sealed it. Every massive body has a boundary called the tidal limit, the distance within which its gravity pulls harder on the near side of a visitor than on the far side, harder than the visitor's own gravity can resist. Cross that line, and a small body is not crushed but pulled apart, stretched until it comes undone. On one low swing, the captured comet crossed Jupiter's tidal limit, passing close over the cloud tops, and the planet's gravity took it in both hands. The comet did not explode. It simply came apart, shedding itself into a procession of fragments, around 20 of them, each a mountain of ice, each trailing its own tail of dust. When telescopes on Earth finally found it, the sight was unlike anything in the sky's recorded history, a chain of glowing pieces strung along their shared orbit, evenly spaced, sailing together through the dark. Observers called it a string of pearls. By the end, the train of fragments stretched across several million kilometers, a comet converted into a line of separate mountains, falling in formation. And here is what gave those months their particular gravity. The arithmetic of the orbit was unambiguous. Every fragment's path could be computed, and every computation agreed. The string would come around once more, and this time it would not miss. For the better part of a year, astronomers on Earth knew, with certainty, that they were watching a countdown. Nothing could be done, and nothing needed to be done, because the target was not Earth. All humanity had to do was watch. Every major observatory on the planet made its preparations. A spacecraft, then traveling through the outer solar system, was turned to look. For the first time in the history of our species, we knew the time and place of a cosmic catastrophe in advance, and we gathered to see it. The fragments arrived over the course of most of a week, falling one after another like a slow drum roll. Each one came down at roughly 60 kilometers per second into the southern hemisphere, and each impact released energy measured in the millions of megatons, which is to say, each single fragment delivered many times the energy of every weapon humanity has ever built, detonating at once. By an accident of geometry, the impacts landed just beyond the edge of the visible disk, barely out of direct sight, and this produced one of the most dramatic effects imaginable. The fireballs rose so high, thousands of kilometers above the cloud deck, that their tops lifted into sunlight and were seen from Earth, plumes of incandescent gas climbing over the planet's limb. And then Jupiter's own rotation did the reveal. The 10-hour spin carried each fresh wound around into full view within minutes, so telescopes watched the impact sites rotate into sight one by one, dark and new, like a slow procession of verdicts. There was one observer with a better seat than any on Earth. A spacecraft, then crossing the outer solar system on its way to Jupiter, happened to view the planet from an angle that exposed the far side, the hemisphere where the fragments would actually strike. While every telescope on Earth waited for the wounds to rotate into view, that distant machine watched the impacts themselves, catching the direct flashes as mountain after mountain of ice met the atmosphere and detonated. Its images, radioed home across hundreds of millions of kilometers, are the only direct records of the strikes ever made. One small camera, built by human hands and still years from its destination, was the sole witness to the largest explosions ever observed in the solar system. What the telescopes on Earth showed, once the planet's spin brought the aftermath around, was hard to believe at the time, and remains so. Each impact left a scar, a dark smudge of shocked and sooty material spread across the cloud tops, ringed by expanding waves that rippled outward through the atmosphere like rings on a pond, waves that scientists later used to probe the hidden layers beneath. The scars were not small. Several exceeded the size of the Earth. For months afterward, the most prominent features on Jupiter were not the belts, not the zones, not even the Great Red Spot, but the chain of dark bruises left by a comet, plainly visible in modest amateur telescopes, the darkest markings observed on the planet in the entire era of telescopic astronomy. The impact salted Jupiter's high atmosphere with water and other compounds that instruments could still detect years later, a chemical residue lingering long after the visible marks had gone. And then, this is the part worth holding, the marks went. The winds smeared the scars, spread them, thinned them, and within months, the clouds had folded over every trace. The atmosphere healed completely, as an ocean closes over a dropped stone. Now set the comparison beside it, gently, because it belongs here. A single one of those 21 fragments, arriving at Earth instead, would have been a catastrophe of the class that ended the age of dinosaurs. A global winter, a broken biosphere, a boundary line in the fossil record. Earth received in its own deep past one such blow, and carries the crater and the extinction to this day. Jupiter took 21 of them in a single week, and within a season, it bore no mark at all. The event that would define the history of any rocky world was, to Jupiter, weather. That is the measure of the world we have been describing all evening. Not that it destroys, though it does, but that it absorbs destruction without noticing. If this were a single freak event, it would still be worth the telling. But the deeper lesson of the string of pearls is that it was not unique. It was merely the time we happened to be watching. In the years since, Jupiter has been struck again and again. One later impact, discovered not by any space agency but by an amateur astronomer at a backyard telescope, left a dark scar the size of an ocean. Observers with modest equipment have repeatedly recorded sudden pinpoint flashes on Jupiter's disk, lasting a second or two, each one an object the size of a house or larger, meeting the atmosphere and vaporizing, explosions in the megaton range, witnessed from suburban gardens. Statistical studies suggest that Jupiter is struck by significant objects at hundreds of times the rate Earth is, for the simple reason we have already learned. Its gravity gathers the traffic. Objects large enough to end a civilization's peace arrive at Jupiter not once in geological ages, but every few decades to centuries. The feeding, in other words, never stopped. We watched it happen once, with every telescope we had, and the fragments strike on, mostly unobserved, in the ordinary course of the giant's weather. One more legacy deserves mention, because it touches our own world directly. Those months of watching changed policy on Earth. The sight of Earth-sized scars on another planet moved the question of cosmic impacts from the margins of science into parliaments and space agencies. The systematic surveys that now sweep the sky every night, cataloguing the near-Earth asteroids and computing their paths decades ahead, trace their support, in large part, to the impression left by that 1 week. It is a strange debt. The clearest demonstration of impact violence ever witnessed was also the beginning of our first serious effort to protect ourselves from it. Jupiter, by taking the blow in front of us, taught us to watch our own sky. The lesson was free this time, and we took it. We have spoken of armored orbiters and doomed probes in passing, as the dangers required. Now let us give the visitors their own chapter, told in order, because the history of our journeys to Jupiter is a single long story with a clear shape. It is the story of a species learning, one mission at a time, how close it is allowed to stand to the largest thing its star ever made. Only around 9 or 10 spacecraft have ever reached Jupiter at all. Most of them did not stay. They swept past at speed, took what measurements they could, and used the giant's own gravity to fling themselves onward, borrowing strength from the very world they were careful not to trust. Each visitor left the next one a lesson, and the lessons, laid end to end, are the curriculum of humility that this whole episode has been reciting. The first attempt was an act of considerable courage. When the earliest probe was dispatched toward Jupiter, 2 obstacles stood in the way, and both were unknowns. The first was the asteroid belt. On the maps of that era, the belt was drawn as a barrier, a river of tumbling stones circling between Mars and Jupiter, and no machine had ever tried to cross it. Some feared the little craft would be sandblasted to pieces. The crossing, when it came, was almost eventless. The belt, as we have seen, is mostly emptiness, its millions of bodies scattered through a volume so enormous that a traveler could cross it 1,000 times and touch nothing. The first fear dissolved on contact with reality. The second fear inverted. Jupiter's radiation, known only from its distant radio glow, had been estimated, and the estimates were wrong. As the probe swung low over the cloud tops, its counters climbed past every prediction, and in the space of hours, the machine absorbed several hundred times the dose that would kill a person. Instruments glitched. False commands fired spontaneously inside its logic. Images came back streaked and marred. The craft survived, narrowly, and radioed home the single most consequential measurement in the history of outer planet exploration, the true ferocity of Jupiter's belts. Its twin, arriving a little later, was retargeted on the strength of that warning, crossing at a more respectful distance. The first visitor took the wound. Every mission since has flown inside the safety of its lesson. Then came the pair of travelers whose names became synonymous with the outer solar system, the 2 probes of the Grand Tour, which reached Jupiter within months of each other and transformed it from a banded disk into a world. Their portraits of the clouds are the images most of us still carry: the marbled storms, the swirling wake, the great red spot resolved at last into a turning, textured engine. They found Jupiter's faint ring, a delicate band of dust no telescope on Earth had ever seen, proof that even the giant keeps some ornaments in miniature. They recorded lightning flickering in the nightside clouds and auroras crowning the poles. And they delivered one of the great surprises in the history of planetary science. On the innermost large moon, in a navigation image taken almost incidentally, an engineer noticed a faint crescent standing off the edge of the disk, where nothing should have been. It was a volcanic plume, caught in the act, rising hundreds of kilometers above the surface. The moon was erupting, live, as the spacecraft flew past. Active volcanism beyond Earth, the first ever witnessed, was discovered not by plan, but by attention, in the margins of a photograph taken for steering. The travelers lingered only briefly, protected by their speed, and then Jupiter's gravity gathered them up and threw them outward, one toward Saturn and on to the ice giants beyond, the giant serving, as it so often has, as the stepping stone it also guards. The next chapter belongs to the Resident, the first spacecraft ever to stay. Arriving after a 6-year journey, it took up orbit and remained for nearly 8 years, circling the system again and again, threading its way among the great moons through dozens of close encounters. Its residency was productive beyond any reasonable hope, and it was also, from the first year, a study in endurance. Its main antenna, the great umbrella that should have poured data home in torrents, never fully opened, its ribs seized, most likely because its lubricants had degraded during the years of storage and travel. The mission seemed crippled. It was rescued by ingenuity at a distance, engineers rewriting the spacecraft's software across hundreds of millions of kilometers, teaching it new compression schemes so that its small spare antenna, a trickle where a river was planned, could still deliver the essential discoveries. And deliver it did. The hidden ocean of the ice moon, the magnetic field of the giant moon, the endless resurfacing of the volcanic moon, the composition of the clouds, all of it came home through the whisper of that backup antenna. Meanwhile, the radiation did its steady work, glitching cameras, stalling the onboard recorder, tripping safe modes, wearing the machine down year by year, until, several times past its design dose, the old Resident was steered into the clouds and ended, deliberately, for the sake of an ocean it had itself revealed. Its passenger deserves its own remembrance. Released months before arrival, the small atmospheric probe made the only deliberate entry into Jupiter ever attempted, and its hour of work was among the most extreme feats in the history of engineering. It struck the atmosphere at about 47 kilometers per second, the fastest atmospheric entry ever flown, and in the first 2 minutes endured deceleration exceeding 200 times Earth's gravity, while the shock ahead of its heat shield burned at temperatures twice as hot as the surface of the Sun. More than half the shield's mass burned away. Then, its violence spent, the probe hung from a parachute and drifted down through the brightening decks for nearly an hour, sampling winds, chemistry, and lightning static, reporting steadily until the pressure passed 22 atmospheres and the heat took its voice. One footnote keeps its scientists honest to this day. By chance, the probe fell into one of the driest, least cloudy regions of the planet, a rare clearing in the global weather, so its readings describe an unrepresentative patch of a world with 300 times Earth's surface area. Our only direct taste of Jupiter sampled, in effect, almost nothing of it. The giant granted one interview and arranged, by accident or not, to be misquoted. The present Resident we have already met in its armor, the polar orbiter with the titanium vault and the diving orbit. Set beside its predecessors, what distinguishes it is how much of the hidden planet it has managed to weigh and map from its brief, repeated plunges. It measured the gravity field finely enough to reveal the fuzzy, diluted core and the depth of the great winds. It mapped the lumpy, tilted magnetic field closely enough to expose the shallow dynamo and the strange, isolated patch of field near the equator. It looked down on the polar cyclone rings no one had predicted, detected the deep roots of the storms, found the ammonia and water mushball weather, and traced the auroras to their power sources in the planet's spin and its moon's breath. Nearly everything in tonight's episode that concerns the interior, the poles, or the depths of the storms was purchased by that one machine, a few irradiated hours at a time, on a lifetime measured in accumulated dose. And the next visitors are already committed. One, the flyby Dodger, is on its way to census the hidden ocean through dozens of fast passes. Another, from a different continent, will tour the system and then settle into orbit around the great shielded moon, the first spacecraft ever to orbit the moon of another planet. The siege continues, more patient and better armored with every generation. Seen whole, The ledger of visitors carries a quiet irony. Jupiter has damaged, worn, or destroyed nearly every machine we have sent into its keeping, and yet it remains the single most generous force in the history of deep space travel because of the slingshot. A spacecraft that swings close to Jupiter can steal a fraction of the giant's colossal orbital momentum, arriving with one speed and leaving with a far greater one, flung outward like a stone from a sling. Jupiter has thrown our envoys to Saturn, to the ice giants, out of the solar system entirely. The fastest and farthest objects our species has ever made owe their speed to its gravity. Even the missions that fear Jupiter borrow from it. It is the ladder we climb to leave the sun's neighborhood, and it asks no permission and takes no notice. The most dangerous planet is also the door. And so we come to the last part of our accounting, the part where we step back from the storms and the belts and the armored machines and ask what all of it finally amounts to. We have spent this night establishing, carefully and honestly, that Jupiter deserves its reputation. It is the most dangerous world the sun keeps. But the shape of that danger matters, and seen from a calm distance, its shape is not what the word suggests. Jupiter is not violent the way a predator is violent. It has no aim, no appetite, no attention. Every hazard we have described tonight, every one, is the unfolding of a single number, the planet's mass, expressed through 4 channels that physics provides. Mass becomes pressure, and pressure forbids any flaw. Mass gathers spin, and spin whips the storms and the field. Mass drives the dynamo, and the dynamo breeds the radiation. Mass reaches outward as gravity, and gravity rearranges worlds. That is the entire machinery of the monster. It is one number, wearing 4 costumes. Nothing in it ever chose anything. Jupiter is not malicious. It is indifferent, on a scale that only physics ever reaches, and indifference at that scale is simply what danger looks like when nothing is intended by it. And it has been exactly this way for longer than the mind can properly hold. The radiation belts were humming before Earth had oceans. The great winds were circling before the first cell divided in whatever warm water it began in. Storms like the Great Red Spot, whether that one or its ancestors, churned through the age of the dinosaurs, through the ice ages, through the first fires and the first cities, and every night of every human life ever lived. The same gravity that starved Mars and scattered the asteroid belt is, tonight, quietly bending the path of some comet you and I will never hear of. Nothing about the giant has paused or softened in 4.5 billion years. Its constancy is total. And there is, if you let there be, something restful in that. Of all the things in the sky, Jupiter is among the least likely to surprise anyone. It is dangerous the way a mountain range is dangerous, and permanent the way mountains only wish they were. The accounting also carries a column we have barely mentioned, the debts. It is fair to say the monster has been, on balance, a strange kind of benefactor. Its early rearrangements helped set the architecture within which Earth formed, and helped direct the traffic of icy bodies that may have delivered much of our water. Without its particular voyage, inward and back out, the inner solar system might hold a crowd of large, hot worlds and no Earth at all. Every mission we have ever flown to the outer planets climbed outward on Jupiter's gravity. The moons it torments are the most promising nearby cradles for a second origin of life, their oceans kept liquid by the very kneading that makes them captives. And the planet's own interior is the best preserved archive that exists of the original cloud from which everything here was made. The hydrogen and helium inside Jupiter are the sun's ingredients, held cold and unburned, a sealed sample of the beginning. The calcium in your bones and the iron in your blood were forged in stars, but the substance of Jupiter is older still, the raw stock of the nebula itself. When we study the monster, we are reading the earliest surviving page of our own story. It has been holding it for us, unaltered, the entire time. It is also worth remembering how close it is, as the universe measures things. At its nearest, Jupiter stands about 590 million kilometers away. Light crosses that gap in a little over half an hour. Cosmically speaking, the most dangerous planet in the solar system is in the next room, near enough to study in detail, far enough that not one of its hazards can ever touch this world's night. That distance is the whole reason tonight's accounting can be restful instead of alarming. Every terror we have described is real, and every one of them is, from here, purely a matter of knowledge. The pressure crushes nothing of yours. The radiation touches no one. The gravity that redirects comets holds Earth gently in the pattern it has held for eons. We are, with respect to Jupiter, in the safest seat in the house, and we have the extraordinary luck of a front-row view. Human beings have, in fact, been watching from that seat for the whole of history. Jupiter is so bright that no generation ever missed it. Ancient sky watchers in unrelated cultures, with no contact and no shared language, independently gave it their chief god's name, as if its rank could be felt long before it could be measured. Its slow, stately orbit, 12 years to circle the sky, made it a calendar for civilizations that used its passage through the constellations to count their years. The deadliest planet has spent most of human history employed as a timekeeper, and it kept excellent time. And it still belongs to everyone. On any clear night when it is up, no instrument is needed to find it, and the smallest telescope shows its moons. A meaningful share of the impact flashes and storm changes on Jupiter are discovered, even now, by amateurs at backyard telescopes, patient people in gardens, watching the giant because watching it is a pleasure. The most dangerous world in the solar system is also the most democratically observed. It has never once been hidden from anybody. There is a wider lesson in it too, one we are only beginning to appreciate as we survey other stars. When astronomers weigh a newly found planetary system, one of the first questions they ask is where its Jupiter sits, because that, as we have seen, decides so much of what a system becomes. A giant on a distant, calm, circular orbit can shepherd its inner worlds and leave room for quiet planets with long histories. Giants that migrated inward, the hot Jupiters we find huddled against their stars, testify to systems where the great mass swept inward and stayed, scouring the orbits where temperate worlds might have lived. Around every sun-like star, some version of the dice we survived is being rolled. Whether a small blue world gets its billions of quiet years appears to depend, in no small part, on the manners of its giant. Ours wandered, turned back, and settled in the outer dark. It did some damage on the way, and it left room. Here we are, in the room it left. As for the future, the giant will keep its post long after this night, and long after all nights that concern us. It is settling and cooling with perfect patience, 2 centimeters a year, and it will still be dimming, still turning its storms, when the sun itself begins to fail. When our star swells into its red old age, billions of years from now, the inner worlds will fare poorly, but Jupiter will remain, singed and enduring, and when the sun finally subsides into a white dwarf, Jupiter will very likely still be there, circling the remnant, the most massive survivor in a diminished kingdom, the last king standing. Its 2 swarms of captive asteroids will still hold their formations. Its comet families will still keep the orbits it assigned them. The bookkeeping of its gravity will go on being honored when every ledger on Earth is dust. Few things we can point to tonight are as close to permanent as this planet. It was here before anything that lives, and it will outstay everything that reads its light. So let us end where we began, with the bright, steady, cream-colored point of light in the night sky. It is the same light your grandparents saw, and theirs, back through every generation to the first upturned faces. Nothing about it warns you, and now you know that everything beneath it would astonish you. Under that gentle light are the storms that outlive nations, the ocean of glowing metal, the field wider than the sun, the belts that close a whole region of space, the gravity that decided the fates of worlds. And none of it, not one particle of it, requires anything from you tonight. Jupiter asks nothing. It notices nothing. It simply continues, as it always has, enormous and constant in the dark, the strongest thing the sun ever made short of itself, resting in plain sight among the stars. And so we leave Jupiter where it has always been, steady in the outer dark, asking nothing of the worlds it governs. It will keep its storms and its captives whether we watch or not, and it will keep them well. Let your shoulders soften now. Let your breathing find its slowest rhythm, and let the night hold the watch for you. Sleep well, and good night.